Now in this lecture we'll find out the radius of a circle. In the drawing we have quadrilateral ABCD that is inscribed by this circle. You know that the diameter of this circle is AC. In addition, you know that side AB equals to side BC, or quadrilateral ABCD. We know that the perimeter of this quadrilateral ABCD is equal to 18 units in its length. The perimeter of a quadrilateral is the sum of its side lengths. That is to say, it is AB plus BC plus CD plus DA. In total, it equals to 18 units. In addition, we know that the area of this quadrilateral ABCD is equal to 36 square units in its size. Again, our task is to find out the radius of this circle. So first of all, we define the sides of this quadrilateral ABCD with letters. We define side AB as A. And because of the fact that side AB equals to side BC, side BC must be also equal to A. We find side AD as B and side CD as C. In the next step, we'll implement rule 7 in our drawing. I'll click quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees inside. So in the drawing, we have a circle. This is peripheral angle ADB that subtends on chord AB, that is the diameter of this circle. And therefore, according to this rule 7, peripheral angle ACB must be equal to 90 degrees inside because it subtends on the diameter of the circle. So any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees inside. So we can implement rule 7 in our drawing. What put in our drawing? We have peripheral angle ABC that subtends on chord AC, that is the diameter of the circle, and therefore according to rule 7 is equal to 90 degrees in its size. Likewise, this is peripheral angle ADC that subtends on chord AC, that is the diameter of the circle, and therefore is equal to 90 degrees in size, according to rule 7. So in the next step, we'll implement the Pythagoras theorem on this right triangle ABC, and then in the right triangle ACD. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, in the right triangle ABC, the hypotenuse is AC. Here by PT is the derivation from Pythagoras theorem. So, according to the Pythagoras theorem, in this right triangle ABC, AC squared, that is the square of the hypotenuse, will be equal to AB squared plus BC squared. So, as you know, AC squared, that is the square of the hypotenuse, is equal to AB squared plus BC squared. And again, in the right triangle ABC, according to the Pythagoras theorem, the following equation is true. That AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. So AC squared equals to AB squared. AB is A, therefore AB squared is A squared plus BC squared. BC is also A, therefore BC squared is A squared. So in total, I should find out that AC squared equals to A squared plus A squared, that is 2A squared. Likewise, we'll implement the Pythagoras theorem on this right triangle, triangle ADC. According to the Pythagoras theorem, in this right triangle ADC, AC squared, that is the square of the hypotenuse, will be equal to AD squared plus DC squared. In the right triangle ADC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AD squared plus DC squared. So AC squared equals to AD squared. AD is B, therefore AD squared is B squared plus DC squared. DC is C, therefore DC squared is C squared. So in total, we should find out that AC squared equals to B squared plus C squared. In the next step, we will create the third equation that states that AC squared, according to equation 1, must be equal to AC squared according to equation 2. So AC squared according to equation 1 equals to 2A squared, and it must be equal to AC squared according to equation 2. AC squared according to equation 2 equals to B squared plus C squared. So in total, I should find out that according to equation 3, 2A squared equals to BC squared, to B squared plus C squared. Again, 2A squared equals to B squared plus C squared. Here we divide this equation by 2, equation 3. You get finally that according to equation 3, A squared equals to B squared plus C squared over 2. But again, according to equation 3, I should find out that B squared plus C squared over 2 equals to A squared. We know that the perimeter of this quadrilateral ABCD equals to 18, so AB plus BC plus CD plus AD equals to 18. AB plus BC is A plus A, that is 2A. So 2A plus B plus C, in total it is equal to 18 according to what is given in the question. Let's read again. According to equation 4, we should find out that it is given in the question that the perimeter of quadrilateral ABCD equals to 18 units, that is to say 2A plus B plus C equals to 18. It is given as a question that the area of this quadrilateral ABCD equals to 16 square units. Actually, quadrilateral ABCD consists of 2 right triangles, and therefore the area of triangle the area of quadrilateral ABCD was equal to the sum of the areas of the 2 shapes that it consists of. That is to say, the area of this quadrilateral ABCD was equal to the area of the first shape that it consists of. That is actually the area of this right triangle ABC plus the area of the second shape that it consists of, that is the area of this triangle AB, right triangle ABC. So now we found out that the area of quadrilateral ABCD is that it equals to 16, and it actually equals to the sum of the areas of the two shapes that it consists of. That is to say, it equals to the area of the first shape, that is actually the area of this right triangle ABC, plus the area of the second shape that it consists of, that is actually the area of this right triangle ADC. So we know that the area of quadrilateral ABCD equals to 16, so we substitute the area of quadrilateral ABCD by 16. So according to equation 5, 16 equals to the area of triangle ABC. What is the area of this triangle ABC? The area of triangle ABC must be equal to the base AB, that is A, times the height BC, that is also A, divided by 2. So it is A square over 2. The area of this right triangle ABC equals to A square over 2 square roots in its size, plus the area of the second shape that ABC consists of, that is the area of this right triangle ADC. The area of this right triangle ADC equals to the base AB, that is B, times the height DC, that is C, over 2. So it is BC over 2. So in total, according to equation 5, we found out that 16 equals to A square over 2 plus BC over 2. Here we multiply this equation by 2. Again, that according to equation 5, (16) times 2 is 32 equals to A square plus BC. Repeat again, according to equation 5, we found out that 32 equals to A square plus BC. But we already found out that A square, according to equation 3, A square equals to B square plus C square over 2. So we substitute A square in this equation 5 by B square plus C square over 2. And again, this equation 32 equals to A square plus BC. So we substitute A square in this equation by B square plus C square over 2 from equation 3. So according to equation 5, we found out that 32 equals to A square. A square, according to equation 3, is B square plus C square over 2. And here also plus BC. So we found out that 32 equals to B square plus C square over 2 plus BC. So here we multiply BC by 2 and then we divide it by 2 in order to account for of this expression. And get that according to equation 5, 32 equals to B square plus C square over 2, and BC times 2 is 2BC divided by 2. We multiply BC by 2 and then we divide it by 2. So total we have here 2 times BC. So total we found out that 32 equals to B square plus C square plus 2 times BC over 2. Here we multiply this equation by 2. And finally we get that 32 times 2 is 64. So 64 equals to B square plus C square plus 2 times BC. And again, according to equation 5, 64 equals to B square plus C square plus 2 times B times C. We know that B square plus C square plus 2 times BC is equal to B plus C square. According to the algebraic identity, this says that A plus B square equals to A square plus B square plus A square plus C square plus 2 times A times B. Therefore, in total, we found out that according to equation 5, 64 equals to b squared plus c squared plus 2 times bc is b plus c squared. So 64 equals to b plus c squared. Here we take a root out of this equation and finally get that b plus c equals to the square root of 64, that is 8. Total according to equation 5, I should found out that b plus c equals to 8. Again, according to equation 5, found out that b plus c equals to 8. But according to equation according to equation 4, 2a plus b plus c equals to 18. Okay, again, according to equation 2, we only found out that 2a plus b plus c equals to 18. So here we have b plus c. So we substitute b plus c in this equation 4 by 8 from equation 5 because b plus c equals to 8. Again, we substitute b plus c here in this equation 4 by 8 from equation 5 because b plus c equals to 8. And get that in total according to equation 4, 2a and b plus c according to equation 5 is 8, so it is 8, 2a plus 8 equals to 18. So here we subtract 8 from this equation and finally get that according to equation 4, 2a equals to 18 minus 8 is 10. So 2a equals to 10. Here we divide this equation by 2 and finally get that according to equation 4, a equals to 10 over 2, that is 5. So a equals to 5 units in itself. Side AB equals to A and A is 5. Side BC also equals to A and A is equals to 5 units in itself. In the next step, we implement the Pythagoras theorem on this line triangle ABC. And again, we implement the Pythagoras theorem on this line triangle ABC. According to the Pythagoras theorem, in this line triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. Here by PT is a relation from Pythagoras theorem. So according to the Pythagoras theorem, in the right side ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. So AC squared equals to AB squared. AB is A and A is 5, therefore AB squared is 5 squared, that is 25. AB squared in total it is 25. Plus BC squared. BC is A and A is 5, so BC squared is 5 squared, that is 25. So in total we found out that AC squared, that is the square of the diameter of the circle, is equal to 25 plus 25 is 50. So in total AC squared equals to 50. We substitute 50 by 25 times 2. So AC squared equals to 25 times 2. So here we take a root out of this equation and finally get that AC, that is the diameter of the circle, AC equals to the square root of 25 is 5, and inside the root we left only with 2. So in total we found out that AC, that is the diameter of this circle, is equal to 5 times square root of 2 units in its length. Therefore, the radius of this circle, that is the radius that we are looking for in this question, must be equal to the diameter over 2. So the radius R equals to the diameter AC over 2. That is to say it is 5 for square root of 2 over 2. 5 times square root of 2 over 2. So the radius R of this circle equals to 5 times square root of 2 over 2 units in its length, or in terms of numbers, is equal to 3.536 units in its length. And again, if you all know that the radius R of this circle is equal to either 5 times square root of 2 over 2 units in its length, or in terms of numbers, it is equal to 3.536 units in its length. Okay, so finished first of those questions. So in the next step, I'll solve the lecture. Our task in this lecture was to find out the radius of this circle. So in the drawing, we have quadrilateral ABCD that is inscribed by this circle. Okay, again, we have quadrilateral ABCD that is inscribed by this circle. We know that side AB of quadrilateral ABCD is equal to side BC. In addition, we know that chord AC is the diameter of this circle, and we also know that the perimeter of this quadrilateral ABCD is equal to 18 units in its length. The perimeter of a quadrilateral is the sum of its side lengths. That is to say, it is AB plus BC plus CD plus DA. In total, it is equal to 18. And we also know that the area of this quadrilateral ABCD is equal to 16 square units in its size. Again, our task is to find out the radius of this circle. So first of all, we define the sides of quadrilateral ABCD with letters. We define side AB as A, and because of the fact that side AB equals to side BC must be also equal to A units in its length. We define side AD as B, and we define side CD of the quadrilateral ABCD as C. In the next step, we implemented rule 7 in our drawing. Okay, to finish on rule 7, according to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in size. So, in the drawing, we have a circle. Inside this circle, we have peripheral angle ACB that subtends on chord BA. BA is the diameter of the circle. So peripheral angle ACB subtends on the diameter of the circle, and therefore must be equal to 90 degrees in size. So any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in size. Peripheral angle ABC subtends on the diameter of the circle. Subtends on chord AB, that is the diameter of the circle, and therefore it is equal to 90 degrees in size according to rule 7. Likewise, we have peripheral angle ADC that also subtends on the diameter of the circle, that is the chord AB, and therefore it is equal to 90 degrees in size according to rule 7. In the next step, we implement the Pythagoras theorem of those both right triangles. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, in the right triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. After this, according to the Pythagoras one, AC squared equals to AB squared plus BC squared. AC squared equals to AB squared. AB is A, therefore AB squared is A squared. Likewise, BC is also A, so BC squared is A squared. So in total, AB squared plus BC squared equals to A squared plus A squared, that is 2A squared. So AC squared equals to 2A squared. Here, actually, in the next step, we implemented the Pythagoras theorem on this right triangle ADC. This right triangle ADC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AD squared plus DC squared. Again, AC squared, that is the square of the hypotenuse, equals to AD squared plus DC squared. It again, in this right triangle ADC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AD squared plus DC squared. So AC squared equals to AD squared. AD is B, therefore AD squared is B squared. DC is C, therefore DC squared is C squared. So in total, AD squared plus DC squared equals to B squared plus C squared. And again, in total, AD squared plus DC squared equals to B squared plus C squared. So in total, according to equation 2, we found out that AC squared equals to B squared plus C squared. While according to equation 1, we already found out that AC squared equals to 2A squared. So we have two equations with the expression AC squared. In the next step, we created equation 3 that says that AC squared, according to equation 1, must be equal to AC squared according to equation 2. AC squared according to equation 1 equals to 2A squared, and it must be equal to AC squared according to equation 2, that equals to B squared plus C squared. So in total, according to equation 3, we found out that A squared equals to 2A squared equals to B squared plus C squared. Here we divided this equation 3 by 2, and finally found out that A squared equals to B squared plus C squared over 2. It is given us a equation that the perimeter of this quadrilateral ABCD equals to 18 units. That is to say, the sum of the lengths of this quadrilateral, the sum of its side lengths, in total equals to 18 units. That is to say, AB plus BC plus CD equals to plus AD equals to 18. AB is A, BC is also A, so AB plus BC is A plus A, that is 2A, plus CD, that is C, plus DA, that is B. In total, the sum of its side lengths must be equal to 18 units. That is to say, 2A plus C plus B equals to 18. So 2A plus B plus C equals to 18. It is given us the equation that the area of this quadrilateral ABCD is equal to 16 square units in its size. But we know that quadrilateral ABCD consists of two shapes, and therefore the area of quadrilateral ABCD must be equal to the sum of the areas of the two shapes that it consists of. So this equals to the area of the first shape, that is the area of this right triangle ABC, plus the area of the second shape, that is the area of this right triangle ADC. And again, the area of quadrilateral ABCD must be equal to the sum of the areas of the two shapes that it consists of. The first shape is triangle ABC, so it is the area of triangle ABC, plus the area of the second shape, that is triangle ADC, so it is the area of triangle ADC. So it is given as the equation that the area of quadrilateral ABCD equals to 16, so we substitute the area of triangle ABCD by 16, so 16 equals to the area of triangle ABC. What is the area of this triangle ABC? It is equals to the base, that is BC, and BC is A, times the height of the base, that is BA, that is also A, divided by 2. So it is A times A over 2, that is A squared over 2. So in total, we found out that the area of triangle ABC equals to A squared over 2, plus the area of this right triangle ADC. The area of this right triangle ADC equals to the base AD times the height DC over 2. AD is B, DC is C, divided by 2. So in total, it is B times C over 2. The area of the right triangle ADC equals to B times C over 2. So in total, we found out that according to equation 5, 16 equals to A squared over 2 plus BC squared over 2. So here we multiply this equation 5 by 2, and finally found out that 16 times 2 is 32, so 32 equals to A squared plus BC. Again, according to equation 5, 32 equals to A squared plus BC. repeat again. According to equation 5, we actually found out that 32 equals to a squared plus bc. So 32 equals to a squared. We already found out that according to equation 3, a squared equals to b squared plus c squared over 2. So we can substitute a squared in this equation 5 by b squared plus c squared over 2. Yeah, we substitute a squared in this equation 5 by b squared plus c squared over 2, because according to equation 3, a squared equals to b squared plus c squared over 2. So in total, according to equation 5, we have found out that 32 equals to b squared plus c squared over 2 plus bc. So here we multiply bc by 2 and then we divide it by 2 in order to the common factor of this expression. And finally we found out that 32 equals to b squared plus c squared over 2. And we have bc times 2 over 2. So it is 2 times bc over 2. So in total we found out that according to equation 5, 32 equals to a squared, b squared plus c squared plus 2 times bc over 2. Here we multiply this equation 5 by 2, and we found out that 32 times 2 is 64 equals to b squared plus c squared plus 2 times b times c. According to the algebraic identity that states that a plus b squared equals to a squared plus b squared plus 2 times ab, we'll get that b squared plus c squared plus 2 times bc equals to b plus c squared. B plus c squared. So we substitute this expression by b plus c squared. So in total we found out that 64 equals to b plus c squared. Here we took out of this equation 5. We found out that the square root of 64 is 8. So 8 equals to the square root of bc squared is b plus c. The square root of b plus c squared is b plus c. So in total, according to equation 5, we found out that b plus c equals to 8. And according to equation 5, b plus c equals to 8. But according to equation 4, we only found out that 2a plus b plus c equals to 18. So we can substitute b plus c in this equation 4 by 8 from this equation 8. We substitute b plus c from this equation 4 by 8 from this equation 5, because b plus c equals to 8. We did it, and we found out that 2a plus b plus c 8 equals to 18. Here we subtracted 8 from this equation, and we found out that 2a equals to 18 minus 8 is 10. So 2a equals to 10. Here we divided this equation by 2, and we found out that a equals to 10 over 2, that is 5. A bc equals to a is 5. ab is a is also 5. So in the next step, we implemented the Pythagoras theorem on this right triangle ABC. So according to the Pythagoras theorem, in this triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. Repeat again. According to the Pythagoras theorem, in this right triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC squared, that is the square of the hypotenuse, equals to AB squared. AB is 5, therefore AB squared is 5 squared, that is 25. Likewise, BC is also 5, so BC squared is 5 squared, that is 25. So in total, AB squared plus BC squared equals to 25 plus 25, that is 50. So AC squared in total equals to 50. We substitute 50 by 25 times 2, and found out that AC squared equals to 25 times 2. Here we took out of this equation, and finally found out that AC equals to the square root of 25, that is 5, so inside the root we left only with 2. So in total AC equals to 5 times square root of 2 units, and it's done. AC is the diameter, and therefore the radius is the diameter over 2. So the radius R is the diameter AC over 2. So it is 5 times square root of 2 over 2. So in total we found out that the radius that we are looking for in this question, that is the radius of this circle, equals to either 5 times square root of 2 over 2 units in its length, or in terms of numbers, the radius of this circle R equals to 3.536 units in its length. Okay, thank you very much.